Welcome back, welcome back, welcome back. I'm Lisa Blackburn. This is my YouTube channel for everything I want to talk about science and math. And today we are finishing the Unit 4 bonding notes in chemistry class. So we only have a little bit of this left. Usually I like to do the notes all at once, but that just didn't happen this time, did it? So, oh well. Okay, so the next part of our notes, we might have stopped with covalent properties. Tomorrow is your digital learning day. So tomorrow you're going to get a chance to this unit that we're doing. It's not hard, but it is a skill you need to practice. So I'm going to give you a stack of worksheets to practice this. And you're going to get faster and faster and better. But if you don't practice and you just watch me doing this, you're not going to be able to do on the test. Because it's one level of skill to watch me do it, to name these things and to understand it, and it's a whole different level of skill for you to be able to do it. Okay, so tomorrow you're going to do a worksheet on this, and I'm also going to show you a video that explains acid names in more detail. We've talked about ionic names, we've talked about covalent names, and now we're going to talk about names of acids. But you're going to watch a video by Mr. Peterson. He teaches at PC, and that's the magnet school, and he's got a lot of really good chemistry videos, so you're going to get to watch him. It's only maybe a 10-minute video. You'll take notes on it, and I think I'm going to have you submit that one through Canvas, because y'all haven't had to submit much through Canvas. I want to make sure that y'all know how to do it. You take notes, take a picture of it with your phone, hit submit. Not hard, but I want to make sure you know how to do it. But your worksheet you'll be doing tomorrow will be part of your packet. And I might have you turn in your notes as part of your packet too. I don't know. We'll see. Okay, so acid names. How do you name an acid? In general, now there's more to it because of polyatomic ions. Remember, polyatomic ions are atoms that act together as an ion. They're covalently bonded. They share electrons, but together they gain or lose an electron and become an ion where electrons are transferred instead of shared. Did that make sense? Did you follow that a little bit? It'll make more sense as we do the lab. Okay, so acids are different. So in general, how you name an acid is they start with a hydrogen in general. And what makes them an acid is when it gets in water, that hydrogen comes off and is floating around. And the more hydrogens you have, the more acidic it is, the more it will burn you. So they usually start with hydrogen. And then they've got some other non-metal end, like chlorine. So to name it, you do hydrogen plus the anion. Remember, the anion is the negative ion because fire ants are negative and kitty cats are positive. And so the hydrogen is the positive part that comes off. The chlorine is the negative part, it's the anion. But you just say the root of it, and then you add the ending ic, and then the word acid. So HCl, what do you think its name would be?
Hydrochloric acid.
Exactly. Y'all are brilliant. Hydrochloric acid. Does that make sense? Hydrochloric acid.
So you just say the root of the first one?
You say the root of the second one. You say hydro for the hydrogen, and then you say the root of the next one, and then you add the ending ic, and then acid. So there's like hydrofluoric acid, hydrochloric acid, hydrobromic acid. So that's it in general. Okay, but there's a little bit different. There's more rules if it's polyatomic, and we will learn it in a video assignment. Okay, now there's another kind of bond that is called metallic bonds. And remember, they have the ones with the free electrons, and they share all of them. Everybody is sharing their electrons. Remember that we talked about the transition metals are our hippie parents, and the hippie commune, letting their little electrons run wild and free wherever they want to. And that makes the metals have their properties. Good conductors of heat, good conductors of electricity, shiny, ductile, malleable. What does ductile mean?
Stretchable.
What?
Stretchy.
Stretchy. You can stretch it into wires. But you can ductile, you can make it into wires. And malleable, what does that one mean?
Hard.
No. Some metals are kind of soft. What? Very close. You've heard of a hammer called a mallet? So if you hit it with a mallet, it's malleable, it becomes thin sheets. So metalsmiths hit metals with hammer and hammer it out flat, right? So you can make it into sheets. So let's write those properties down. Metals are shiny. Shiny, that's kind of real. They conduct heat and electricity. That's the one ring to rule them all. You could write a little Elvish on the inside, around the outside, or whatever it is. The dark language of the orcs. It's ductile, which means it could be a wire, and it's malleable. Which means it can be sheets. You can have sheet metal. You've heard of that? Okay, there are other forces that are called bonds that aren't real bonds. They are intermolecular forces. They're caused by intermolecular forces. So, really, a lot of times you'll hear that there are only two kinds of bonds, covalent and ionic. But then you have metallic bonds that are kind of like bonds because they're sharing electrons, and metals stick together. Bonds are what sticks atoms together. But in some ways, it's not really bonded. Like when we made our pennies, we made our gold and silver pennies. We made bronze on the outside of our pennies. We bronze coated our pennies. That's not really considered a bond. It's considered a mixture. And mixtures are not bonded. They can continue to have the properties of what makes them up. So our pennies weren't brownish like copper. They weren't silver. They were kind of in between. They were gold. So metals aren't metallic bonds aren't quite real bonds, but they're more of a bond because the electrons are shared. But these new ones that I want to talk about, they're not considered bonds, but they're called bonds because they're really important, and they are what make atoms stick together. Okay, so one of them that's probably the most important one is called hydrogen bonds. Now, there's like a list of these, and I hadn't really planned on. We're trying to cram stuff in because of our STEM unit. But there's really about 5 of these. Y'all probably should be learning about these other intermolecular forces. But I didn't put them here. I just put the most important one, hydrogen bonds, because one, it has to do with our STEM, and 2, it's the most important one. But we might go back and learn the others. There's things called van der Waal forces, things that are fun to say. But we might go back and learn those more later. Because for true honors chemistry, y'all should be learning a little bit more about this. But right now we're not. We're going to just sort of skip over it. But we might go back to it if we have time, which we might. We'll see. All right, so there's this thing called hydrogen bonds. Let me explain it to you. Let's see where you have room on your paper. You should have room like right in there, but I wrote on it. I'm going to do it up here, but you can write it wherever you've got room. Okay, so here's water. Remember, water looks like unimpressed Mickey Mouse or Kermit the Frog. So this is the oxygen, the big head, and it's negative because oxygen is more electronegative. Remember, electronegativity is the ability to attract electrons to oneself. So, or you can think of oxygen just as the bully. Wimpy little hydrogens, not much electronegativity at all. So they are the divorced parents, where it is a bond between a metal and a nonmetal, even though hydrogen's not it's sort of like a metal and a nonmetal, but hydrogen is not really a metal. So we consider this covalent bonds, because the electrons are shared. And that's why on some periodic tables, hydrogen is drawn just floating sort of in the middle above everybody else because it doesn't really fit as a metal or a non-metal. But we're going to think of it as a non-metal. Was that completely confusing? Don't worry about it. Just know that they are sharing their electrons. Oxygen's a bully, it's got it more. That causes water to have a positive head, positive oxygen, and negative, say it wrong ways, positive ears, negative face. With this having different ends, it's called polar because it's got a positive side and a negative side. Everybody remember that from last week? Okay. So what happens is these little positives right here, opposites attract. If there's another water molecule, that hydrogen will line up with the oxygen of a different water molecule, and they'll stick together. This one will go find another negative to line up with, and they'll stick together. This negative will attract some little positive ears, and they'll stick to them. Can you see how it's sticking together now? It's not a real bond because electrons are not shared or transferred between these water molecules. But there is a force of attraction that sticks them together. It is extremely important. You would not be alive if this was not happening. There would be no life. Yes?
So they're not bonded together, they're just attracted together?
They are, exactly. But it's so important, we call it a bond. We call this hydrogen bonding, even though it's not really a bond. It's an intermolecular force, between molecular molecules force, a force between molecules of stickiness, sticking them together. You got your brain around it? Not too hard? Okay. So our example is water, and water is needed for life. Why is it so special? Let me see. It is a sticky molecule. It's a sticky molecule. It sticks to itself. And that's what gives us this characteristic of life. I'm going to scroll up. It makes for great TV viewing when I leave and scroll up. And that's what we're going to do. Seems like if you give it lots of dots and then scroll, it does better. Haha, watch that. Yes. Let's put it in your inbox. All right. Okay, so the reason why it's sticky is it's based on its polarity. Its polarity, the fact that it's got a positive and negative end. And it results in many things that life depends on. So one is trees. We have to have trees to live, right? We have to have plants. What do plants produce that we have to have? Oxygen and food. All food comes from plants. Plants turn sunlight into energy through photosynthesis. Remember that in biology? Remember how it makes the glucose and the Krebs cycle, and the dark cycle, and the light cycle, the Calvin cycle, all those things. Okay, so trees and plants are important for not only their life, but all animal life too. Everybody remembers that? Trees do not have a heart. Have you noticed that? No circulatory system. But yet, there are giant sequoia trees in California, giant loblolly pines here in Georgia. Then somehow they can get water all the way from the ground all the way up to their leaves. How do you think they do that? Did you talk about it in biology class? Did you talk about the xylem and the phloem? Remember that? The xylem and the phloem, the little tubules in the plants. Did y'all get to plants? I know that they really cut the biology curriculum. Y'all don't do a lot of the things we used to do. But anyway, you remember xylem and phloem? The vascular bundles? No. Okay, maybe you didn't get to the xylem and phloem. In trees, in all plants, there are what are called vascular bundles. They're veins, but they're in little vascular, just like our veins, but bundled, they're bundled together, and one transports food to the plant, and the other one transports water. But there is no heart to pump it. So how does the water get from the ground and the roots all the way up to those leaves? It's based on water chemistry. So how it works is there are these little bitty tubes in the trees. Okay. Now remember, when we learned how to read graduated cylinders, we learned to read from the bottom of the meniscus. What do those words mean? What does that mean when I told you to read the graduated cylinder from the bottom of the meniscus? What did that mean? There's a curve, and you read it from the bottom by holding it up to eye level. And you look at the curve, and you read it from the bottom of the curve, not the top. Do you remember that now? When you learned to read this? It was our first unit. Okay, so when water is in a tube, the surface of it will curve. That's the meniscus. And when you read it, if it's a graduated cylinder, you read it from the bottom of the meniscus. That's where it's reading, not the top. In the plants, the tubes are so small. The smaller the tube, the more this curves, deeper and deeper and deeper curve, to the point where the curve is folding in on itself, and the water, just through the force of its electricity, of the negative oxygen and the positive ears, it can crawl up a tube with only using that electrical force. Isn't that cool? That just with electrical force, it can crawl up that tube. And that's how plants drink. The vascular bundles, the tubes of the plants, are so small that the water can crawl itself up just using the force of electricity, of opposites attract. It can crawl up those tubes all by itself. You might have seen this before. If you've ever had to have your blood tested, you know how they'll prick you, like for iron. You go to the pediatrician, and they take that stabber, and they stab your finger, and it hurts, and they squeeze it and make some blood on your finger. Have you ever had to have that done? Then they take something, and they hold it up to the blood, and it's either a little tube or a flat thing, and the blood just goes zoop and sucks into it. Has anybody watched them, or do you always turn your head away? What sucks the blood into that thing is capillary action. This is called capillary action. Very, very small tubes are called capillaries. The smallest tubes of your blood system are capillaries, and it's where the blood only goes one cell thick at a time. And that's where things are exchanged, gases and stuff like that. All right, so everybody understands how trees drink now? If trees couldn't drink, they couldn't do photosynthesis. They have to have water. If they couldn't do photosynthesis, they wouldn't make food for us and oxygen. All life would die if water could not crawl up trees all by itself. Everybody's got that idea in your head? Okay, so trees can drink. That's one of its amazing properties. So if it didn't have this property, no life on this planet or any other planet. Next one is that it is called the universal solvent. And one of our reports we had on water touched on this. Who did water and health? Whose report was that? It was in this class, wasn't it? Didn't somebody do like how long you can live without dying for water and stuff? That wasn't this class. This was the other class who did water and health. Okay, one of the groups did water and health. I really wish y'all could have seen each other's reports because y'all picked different things, and between the two classes, y'all really covered it. Okay, so water is the universal solvent, meaning because it's got this positive side and a negative side, it's really good at attacking stuff and pulling them apart. So you put salt in water, it attacks it and pulls it apart, doesn't it? As soon as you put salt in water, it dissolves, right? The reason why is because the water is attacking it, and the positive side's put into the positive, the negative to the negative and opposites attract, and it pulls it apart. So it dissolves things. A solvent is something that dissolves. So water is great at dissolving everything. If it didn't, there'd be no life, because how nutrients are transported, how life is supported is with dissolving stuff. Remember in biology learning about osmosis? Remember how osmosis is water going across a thin membrane and things can be carried passively through osmosis? Did you learn that? Passive transport, active transport, remember that? So passive transport with osmosis, water can carry things. Water dissolves things like nutrients, and then it carries things where they need to go. It's very important that things dissolve, not only in our bodies, water carrying everything around, but also for just like the oceans. The oceans have all of these nutrients dissolved in it. It supports aquatic life. If the oceans died, would we have life? No. Remember biology, the web of life, how we're all connected, all life is connected, and if one part of an ecosystem dies, it can all die. Well, the oceans are the foundation of biological life. Without the oceans having living beings in it, we would not have life on land either. It's all connected. So, if it wasn't the universal solvent, no life on this planet. I made this list but didn't write down what I was thinking. I think it's important in our bodies because of that. It's important in our bodies to dissolve stuff. Another thing about being the universal solvent is not only can it dissolve things like salt, it's such a powerful solvent, it can dissolve gas. So fish do not breathe water. They don't breathe the oxygen that is bound into H2O. Fish breathe oxygen gas the same way we do, but they breathe oxygen gas that has been dissolved into water. If water wasn't such a powerful solvent, it could not dissolve oxygen gas, all the fish would die. Excuse me. Does that make sense to you? Did you know that fish don't breathe water? I see nods, yes. Very good. Okay. The next one. Why water supports life is water is more dense than ice. Liquid water, that's liquid, lowercase l in cursive by tradition. Liquid water is more dense than ice. Why is life on this planet dependent on that fact? Why is liquid water being more dense than ice? Ice floats. If ice didn't float, we would not have life on this planet. How come? Can y'all figure it out? Yes, Jeff.
Ice floats because when the water starts to freeze, oxygen molecules and other gaseous molecules get stuck in the ice, so it becomes less dense.
Yes, but why is life on this earth dependent upon that fact? Did y'all hear what he said? He said, okay, now this goes back to the way it's shaped like Mickey Mouse. Okay, so when water is liquid, it sticks together really, really hard, really, really close, getting as close as possible. But when it freezes, it has to spread out with the positives and negatives spreading out into its crystal lattice, and it makes little pockets of air in it. Because of the shape, it has to spread out to get into its crystal lattice. It makes pockets of air. So therefore, ice floats. But that's not the question. The question is, why does ice floating, why is life on this planet dependent on that fact? If ice didn't float, none of you would be alive. We'd all be dead. How come? Yes. It has to do with the sea, yes, and lakes and rivers. Jonathan, you got an idea? Got an idea? No, I'm always looking for your eyeballs to make sure you understand. Sam, got an idea? Sam. Give Sam a little nudge. Sam, do you have an idea of why it's so important that ice floats? No. I want to see your eyes. Make sure you're thinking about this. You would not be alive if ice couldn't float. You'd just die if you had your Coca-Cola and your ice sunk to the bottom. You'd drop dead. Not really, but it has to do with the oceans and the lakes and the rivers. What is it? Why would we all die if ice didn't float? What?
The glaciers.
Something about the glaciers.
If they sunk, it would,
Say that it would flood. Probably, but that's not the main thing. Good thought, though. What else? Anybody can figure it out? I know it's early to think about these big questions of life. Say it louder. What?
ice floating in water.
Ice floats in liquid water. If it didn't, we would all die. So why? Why in the world would it kill us if ice didn't float? Yes. Talk louder. What? No. Good guess, but no. Y'all gotta talk loud if you're guessing. Evelyn, you got a guess? No? Okay, so if not, ice would sink to the bottom. That's what most chemicals do. For most chemicals, the solid is more dense than the liquid. Okay, so let's imagine that. Let's imagine that water was a normal chemical that didn't do this, that didn't do the spreading out thing. So here you've got a lake. It's winter. It's starting to freeze. The ice would sink to the bottom. Okay, and then we get a little colder. More ice would sink to the bottom.
Oh, and then it would just no water.
It would what?
Just no water.
It would just be all ice. So what would happen to the fish?
Die.
They'd all die because they would end up flapping on top on a block of ice. Do you see that? But instead, this is what happens. When bodies of water start to freeze, as it gets colder and colder, it gets down to 4 degrees Celsius. Water is most dense at 4 degrees Celsius. So that most dense water goes all the way down to the bottom, and it's 4 degrees. 4 degrees is above zero. 4 degrees is still liquid. Then it gets colder, and it actually starts freezing. Well, then the ice floats up to the top, and it makes a layer of ice on top of the body of water. Underneath, it's more dense, it's still liquid. Ice is an insulator. All those little pockets of air that y'all talked about, of there being in the water, that air is an insulator. So then that layer of ice keeps the rest of the water liquid. It keeps it above freezing. All the little fish are down here happy for the winter with their little insulator layer of ice on top to keep what's underneath from freezing. So that's why you can always do ice fishing, make a little hole, go down there, get the fish. Fish live through the winter. If the bodies of water didn't stay alive, we would not stay alive. Life is based on ocean life. Does that make sense to you? So once again, if water didn't have this property, no life on planet Earth. Another aspect of it. So this is important for bodies of water. The next thing, water. The next thing. Okay, think about our whole Earth. We are the water planet. Over 70% covered in water with the oceans. Now recent research in Japan and Canada have shown that the Earth is full of 2 to 3 times as much water on the inside as it is in the oceans. We are water inside and out. We've got clouds all up in the atmosphere. We are even water in the air. So we're the water planet. So when scientists are looking for life in other planets, they're always looking for one covered in water. Haven't found one yet, but we're always hoping that we'll find some aliens, and hopefully they'll be nice. But it would have to be a planet just like ours, covered in water. Why? Why is life dependent upon our planet being covered in water? Am I making y'all think too much early in the morning? I'm getting yes. Why? Why would we all die if it wasn't covered in water? We only drink 1% of that. So it's not for drinking. Why do we have to have our whole planet covered in water for us all to live? No. Good guess, but no. Yes? Talk louder, Sarah. Yes. It's a connection to the sun. What is it? Yes.
To regulate the temperature?
Yes. Okay. Because water is so sticky, it sticks to itself so hard with those positive and negative attractions. Because of that, it does not like to heat up quickly or cool down quickly. It's a property we're going to learn more about in our heat unit called specific heat. There are certain chemicals that takes them a long time to heat up, and once they heat up, that takes them a long time to cool back down again. And water is the quintessential high specific heat chemical, which means here is our Earth covered in water. Other planets, during the day, it gets so hot it would not support life. And at night, it gets so cold it would not support life. Does that make sense to you? But our Earth, during the day, the sun shines on the Earth, and the water takes that extra energy and turns it into energy to heat up the oceans. The number one thing our sun is used for is to heat up our oceans. So all day long, the oceans take the extra energy so we don't get fried like a crisp and we're not burnt up. So then all day long, oceans keeping it cool and nice. Then the Earth turns around for the nighttime. Other planets at night, it gets so cold you would die, frozen like a popsicle. But not Earth. It turns out at night, then the oceans start giving up all their heat to the Earth. They start giving it back, keeping us perfectly temperature where we can have life. We can have life from Alaska to Ecuador. Never too hot, never too cold. Might be cold, might be hot, but never too hot or too cold for life. Isn't that exciting? It just kind of gave me chill bumps thinking about it. Absolutely perfect. So to have a planet where there's life, it's got to be a watery planet. Does that make sense to you? Can you imagine that? Okay. So this controls the temperature of the Earth. Okay. Okay. So Earth is a water planet. But it's mostly what kind of water? Salt water, which is very good for us having life and the fish and all that. But we need water to drink. We need fresh water. We need fresh, clean water. And this is a worldwide problem, and that's our STEM problem, is even though we have plenty of water, we are the water planet, we don't have enough to drink. It's a worldwide problem. People spend all day trying to get water. People die of waterborne diseases. People die of thirst. People need water for industry. Right now there's a huge thing in the news, I don't know if you've seen it, but Europe and China are having energy shortages where they're having to cut off the power, which means, and water can be used to make electricity. That's how we do it here in Georgia. We have Lake Lanier. Y'all have heard of Lake Lanier, right? And the Beaufort Dam, which is where they have dammed up the water. They let the water go through the dam. It turns turbines. It's like blowing on a pinwheel, and it makes electricity. So water is even connected to the ability to have electricity. And manufacturing and food. They say that it's going to cause a food shortage in Europe because a lot of Europe is in northern latitudes where they don't have long growing seasons like we have here in Georgia. We have a very long growing season. You can get crops in Georgia from spring till late fall. You can still get tomatoes in November sometimes. So we have we can grow collard greens all winter long. We have a great growing season here being in the South. Florida, they can grow year-round. Colombia, South America, they could grow year-round. But up in Europe, they have very short growing season, very short summers. So they grow a lot of their food in greenhouses. The greenhouses need electricity. The electricity is being cut off. They're saying it's going to cause food shortages. That's just crazy, isn't it? Hard to think about. So this is a worldwide problem. Now, so what we need to be able to clean water to be able to drink. So what are some ideas that y'all have? What are some brainstorming ideas of ways that we could purify water? We talked about that a little bit, but let's write them down in our notes. What are some ways we talked about there are ways that we could make dirty water clean so we could drink it? What'd you say? Desalinization. And how can you desalinate water? How can you get the salt out of it? We talked about 2 ways. We could evaporate, right, so we could use distillation, which uses evaporation then condensation. What's another way? Purification. But let's talk about the desalinization in particular. What is a way that did anybody come across in your research of another way besides distillation that they can desalinate water? Yes. Boiling it would be part of distillation. You boil it, you make it into steam, you condense it, and it's pure water. Yes.
It can be purified with gravel and sand.
Filtration, yes, that's another way. Like gravel and sand or filter paper or something like that. That's another way of purified water. What else did we learn in our research? Did anybody learn about membranes, osmosis, actually using osmosis to use a membrane? It would be a filtration way, but in particular you can use membranes also. A membrane where you would force it through. There's some research going on with that, especially in Israel. They've got some new research on how to desalinate. See, we've got plenty of water. The problem is it's salty. You can't drink it, or it's dirty, or it's full of poop, and you can't drink it. So we need poop-free, salt-free, clean and fresh water. So we are going to look at some ways in lab, and that's going to be our STEM unit. You guys are going to come up with ideas to purify water. We're going to get some dirty water, and we're going to try to purify it. That's sort of our problem. That's our task. And what we're going to do is we're going to go, supposedly, there's a creek by the practice field. So if some of y'all know where it is, you can lead the way. We're going to go get some water, and we are going to work on purifying it. All right, so hopefully maybe later this week, but it depends also on the weather. It's supposed to be raining this week, and so we might have to go on with this unit, learn what we're supposed to, and when the weather's nice, just stop and go get our water and keep working on learning how to purify water. And we're also going to do some design things. We're going to talk about different ways to purify water, and we're going to work with some design, coming up with designs. Yes?
Friday's the only day it's not going to rain this week.
Friday's the only day it's not going to, okay, maybe Friday. Friday we might go get our water. And before then we'll talk about different ways that we can use to purify that. Okay, so we have distillation, filtration. What about if there's oil and water? What can we do then? We can separate it, right? There's a thing called a separatory funnel. Separate. I don't know if I spelled that right or not. It's separate, right? Or separate. A separate piece is an A in that book. Well, no, we'll look it up. All right, so we can separate it. There's something called a separatory funnel you can use to take oil off. What about, how can we make it, say it's muddy, how can we make it settle out quickly? If we want to speed up the settling out, how can we do that?
Chemical.
A what?
I think it's called a tumbler.
A tumbler? Something to spin it, maybe? Yes?
Chemicals.
You could also use chemicals. Both of those are good. So there's a thing called a centrifuge, going off Bryson's idea. He called it a tumbler, but he was saying you spin it. So there's this thing where you can like put test tubes in it. You spin it real fast, and it slings the heavier stuff, the dirt, to the bottom. Then you pour off the top. It's called decanting, and you can separate it that way. So a centrifuge is something we can do. Now there is a problem with centrifuge, but we'll talk about that in a second. And what did you say, Max? I wanted to write that one down too. Or was it Hunter? Who just told me one?
Chemicals.
Chemicals, that was it. We could also use chemicals, because even if we get it looking nice and pure, should you trust it to drink it? No. What do they add to water before you're allowed to drink it? When we learned about that in class.
Chlorine.
They add chlorine. Chlorine kills all the germs. It's a disinfectant, all the virus, all the poop, all the bacteria in the poop. It kills it all. So chemicals is another way to do that. Now this is basically how water is purified mostly worldwide. There's a little bit of a problem that some of this doesn't always get gotten, in particular drugs. What happens is people take drugs, not necessarily illegal, but illegal also. Say you're on some medicine. Say you're a lady and you're on birth control because you don't want to have a baby. So you take your birth control pills and then you go pee, and part of that birth control pill will be dissolved, because water being the universal solvent, part of it will be dissolved in your pee, and you will pee birth control pill into the potty, which goes to be cleaned up and then re-released into the water system, where it is reclaimed, cleaned up, and sent back for people to drink. So they say because of drugs, legal and illegal, that we have in our water drugs that we don't mean to be there. So now say there's a lady who's trying to get pregnant. She's drinking her 8 glasses of water trying to be healthy and get pregnant, but in those 8 glasses of water are tiny bits of dissolved birth control pill. Is that going to help her get pregnant? No. So do you see the problem? One of our problems with water is that it's the universal solvent, and it's real hard to get out all the chemicals that we end up putting in it and one of the problems is drugs. A lot of people are on a lot of medicine, aren't they? High blood pressure medicine, antidepressants, all kinds of stuff. People are taking medicine, heart pills, whatever, and those pills end up in the water system, not from people just like flushing them, police, knock, 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 oh, flush the drugs down the potty quick. It's not just that. It's that too, though. But drugs are ending up in our water system. I think it's much better out here in the country. I think city of Atlanta has more problems with this, with more people, and the fact that they have to reclaim their water pretty directly between flushing and drinking. Here, our new water's coming out of the Etowah River, which is coming from the North Georgia mountains. Whole lot less people to be flushing stuff that ends up in the river. So I think our water's a little bit better. So what do y'all think about all that? So what we're going to do is we're going to design ways to purify our water. And the way we want to do it is we also want to learn about the purification process. So probably the fastest, best way to do it would be to go straight for distillation. But distillation is expensive on a municipal scale. Distillation costs a lot of energy cost. So we're going to start with the least expensive way and work our way to a more expensive way of purifying water. How do you feel about that? So we're going to try to go through all of these ways. We're going to try to do all of this to get our water that we're going to go get from the creek pure. And I'm also going to bring you some foul water that I make to purify. that'll come out that'll start off dirtier where you can see it better. I'm imagining this creek water is not going to look really, really dirty. So I'm going to bring you some other water, some foul water that's going to start off looking good and dirty and have plenty in it for us to clean out. Yes?
Free money.
Behind the baseball field, there's like a dirty creek.
A dirty, dirty creek?
Yeah.
Okay, we'll get some of that water too. We might have 3 kinds of water to purify then.
It's the same.
It's the same one as the creek? Okay, so the creek's pretty dirty. That's good. I actually want it to be dirty so we can clean it. The other thing is, the other problem is, y'all listen, is that that we had a centrifuge here at school. Notice I use the past tense, had. When I got hired here last year, I actually got hired for the year before that to be the new forensics teacher, and the day I was supposed to start was March 16th. What happened on March 16th? Everybody got sent home. So they told me they were going to push back my hire date, and they pushed it back to never. So I never got, because we never came back to school, right? So I never got hired for that. But what happened here at this school was everybody left that, whatever it was, 1650, March 13th, they left thinking they were coming back on Monday, and they never came back in the building that year. So the chemistry teacher at that time, not blaming her, she didn't know, she didn't cause COVID, but she left. It was this room, and she just left. Well, there were things going on back in the chemical stock room where reactions were going on. Meanwhile, she went to virtual, and I got hired that summer again to do a different job. So I got hired one more time, and when I walked in here, there was a haze of white smoke coming from the stockroom where something was reacting. The smoke is burning. I don't know what it was. I don't have any idea what chemical was in the air in here. But if you touched stuff, it would make your skin start burning. So I was like, oh no, what a problem. I'm so glad it's not my problem. Of course it was my problem. It became my problem because then I started teaching chemistry and it became my problem. So I worked all last year in cleaning out, figuring out what was bad in the stockroom and getting rid of it and cleaning and cleaning and cleaning. And then the last thing was it at the beginning of this year? Yes, it was at the beginning of this year. I'd gotten all the bad chemicals gone. The science head for the county came and helped clean all the chemical white powder off of everything, the Bernie white powder. She spent all day with custodians cleaning it. There's no more Bernie white powder in the air here. But the last thing was we had some equipment that had been stored in the chemical stockroom. You never store anything but chemicals in a chemical stockroom for this reason. Bernie white powder got over everything. So we had a centrifuge, and I was like, oh yay, and I got it, and I put it in that storage room right there, and I plugged it in to see if it still worked, and at first it didn't, and then it suddenly started, and a huge puff of Bernie white chemical came out of it. I unplugged it and threw it away. So we don't have, because whatever that Bernie white powder is, had not only was it in it, and I'm not taking this machine apart to try to clean its inside guts. When you spin it, the chemical would come out. But this chemical, whatever it is, it was reacting with metals. It was burning holes in the metal shelves, and I had a metal file cabinet back there it burnt holes in. I mean, it was just the biggest mess. My son came and helped me clear it all out from Georgia Tech. What we were doing, okay, we were wearing the gloves, the whole outfit, and as we were going through cleaning stuff, we would touch stuff, our glove would start turning brown, black, and then start getting holes in it. So we were constantly burning through gloves. Who knows what this chemical was, but it was something nasty. So we finally got all cleared out. So I threw the centrifuge away. So we don't have a centrifuge, but we would like to use a centrifuge. So I have found where students, and this is your sort of exciting STEM project, where students have designed centrifuges out of salad spinners. So you take a salad spinner and you design it to be able to hold test tubes so you can spin it. So that's what. So we're getting a couple of salad spinners, a couple of different models that the bookkeeper, Miss Mann, is getting for us. And as soon as she gets them, we're going to see if we can design in your design teams. This is where we're gonna start using our STEM journal. We're going to use our STEM journal to record the water project, to record your designs for filtering the water, for separating the water, for centrifuging the water. You're not really going to design the chemicals. You don't know enough. And you're not going to design the still, because stills have to be made out of special glass, and I bought one for us. So with the STEM project, there was some money, and one of the things I bought was a distillation apparatus. They're real expensive, hundreds of dollars, but we got one, and we'll be able to use it. But the others, you are on your STEM journals, that's what you're going to be designing. You're going to be designing ways, if you filter it, how are you going to filter it? What are you going to put in your filtration? Justine said you could use sand. Isn't that what you said, Justine? You could use sand. So in her design, she might want to try putting her water through sand. Are there other things you could put your water through? Do you see? You're getting the vision now of the STEM project? Yes.
I built a water filter in the 6th grade for a science project.
Excellent. Prior knowledge. You should write out stuff about that. Excellent. Always build off of prior knowledge. That's great. So you sort of see what we're doing now? Then later in your math classes with Dr. D'Amberville, you are going to revisit filtration and see if you can do it better. We're going to do whatever we got. Styrofoam cups, sand, whatever y'all come up with, we're going to use what we've got and come up with some ways to filter it. But with Dr. D'Amberville, you're going to do a little bit more in-depth research and ways to do filtration. And then with Mr. Hall, you're going to do more about the chemicals in water and things like pH. Acidity, basicity. You wouldn't want water that's extremely acidic, would you? Or basic, either one. Now, slightly basic water is supposed to be more healthy, according to the chiropractors. Have y'all heard that? They say it's good for you to have slightly basic water. But y'all can learn more about that with Mr. Hall. So that's sort of an overview of our STEM project. You kind of got a better idea of where we're going now and what we're doing with our water? Okay, now, few last little ideas to our notes. I'm going to scroll up and we'll finish the last little bit here. Okay, so there are a few other little ideas. One is, do you remember what I told you Vesper is? Not Vespa, the little thing you can ride around, but Vesper. Do y'all remember what that is? It had to do with our marshmallows and pretzels. That delicious activity we did. No? Okay, so what it is, remember that our pretzels were negative, and what do likes do? Attract or repel? Things are alike, attract or repel? Repel. So Vesper is basically that these electron clouds try to get as far away from each other as possible because they're negative. So then also, do you remember what I told you a polyatomic ion is? Poly means many. So atomic, many atom, ion. So what's a polyatomic ion? A lot of atoms stuck together with covalent bonds, but then together they act like an ion and form ionic bonds. So one thing is Vesper applies to polyatomic ions too. They get their shape from those electron clouds trying to get away from each other. And also there are exceptions to the octet rule. And we talked about that a little bit, didn't we? We talked about carbon, it how it doesn't just do, it would rather have half-filled orbitals than a filled orbital and a partially filled orbital. There are other exceptions. There are some atoms that can be forced to have more than 8 electrons, and you get these really weird looking structures that are there sometimes. So when you see those in college, don't say, Miss Blackburn said they always want 8. Not always. There's always some exceptions, right? Right? All right, so that's the notes for this unit. I'm thinking a test next Monday, a week from today. But between now and then, we have a lot of practicing to do. So we got labs, we have worksheets, we might take a field trip down to the creek. So we have a lot to do. So put away your notes and we're going to do an activity now. Like, share, subscribe.